Group activity recognition (GAR) aims to classify collective activities from videos, which is essential for video understanding and has various applications. Existing RGB-based methods encounter challenges such as background variations, occlusions, and significant computational overhead. To overcome these limitations, the authors propose a novel approach using a panoramic graph that incorporates multi-person skeletons and objects to encapsulate group activity. This graph enables Graph Convolutional Network (GCN) to unify intra-person, inter-person, and person-object interactive modeling through spatial-temporal graph convolutions. The panoramic graph represents a group activity as a collection of multi-person skeletons and object keypoints, leveraging the strong prior of the skeletal graph to enhance feature extraction capabilities of spatial and temporal graph convolutions. The authors develop a pipeline that extracts skeleton coordinates using pose estimation and tracking algorithms and employs Multi-person Panoramic GCN (MP-GCN) to predict group activities. The proposed MP-GCN method achieves state-of-the-art performance in both accuracy and efficiency on volleyball and NBA datasets, outperforming RGB-based approaches by using only estimated 2D keypoints as input. This approach offers an effective alternative to RGB video, providing a lightweight and informative representation of human motions without requiring accurate individual annotations and specialized interaction reasoning modules. The paper presents a novel pipeline for skeleton-based group activity recognition, leveraging pre-trained pose estimation and object detection methods to extract keypoints for both humans and objects. A reassignment strategy coupled with pose tracking algorithms is developed to enhance consistent identity assignments across frames. The proposed method, MP-GCN, outperforms state-of-the-art keypoint-based methods on volleyball, NBA, and kinetics datasets with significantly lower computation cost compared to RGB-based methods. The authors review related work in group activity recognition, highlighting the challenges of video-based methods and the potential of using pose data as an alternative. Here is a combined summary of the 4 pages. This research proposes a novel approach to group activity recognition in videos, leveraging a multi-person object graph that integrates human and object information into a panoramic view. The authors introduce an undirected graph G, which includes end joints and several bones to represent a person's body, and incorporate object keypoints to form a human object graph. Graph convolution is employed to capture spatial relationships among skeleton joints within a single frame and temporal dependencies across multiple frames, using spatial graph convolution (SGC) and temporal convolution network (TCN) layers. The SGC operation applies a weight function to categorized neighbor nodes and uses a normalizing term to balance the influence of different subsets. The authors present a multi-person graph, viewing all individuals in a scene as a unified group, and introduce the panoramic multi-person object graph, which integrates human object and multi-person graphs. This holistic representation of group activity is used in the architecture of MP-GCN, comprising basic blocks that include SGC layers and TCN layers to extract information embedded in the multi-person object skeleton graph. The approach effectively recognizes group activities by leveraging spatial and temporal information from the panoramic graph. The MP-GCN model is designed with an early fusion strategy, incorporating 4 input branches for joint, bone, joint motion, and bone motion data, reducing complexity compared to conventional ensemble solutions. The basic block consists of a spatial graph convolution, SGC, multi-scaled temporal convolutional network, TCN, and spatial temporal person attention block with module-wise residual links. The SGC operates on the entire panoramic graph, maintaining the graph scale throughout the network, while the TCN captures temporal dynamics in consecutive frames. The spatial temporal person attention module computes attention scores for individuals across frames, enabling the MP-GCN to focus on key individuals and objects in crowded scenes. The paper also discusses a tracking-based pose reassignment strategy to enhance data consistency and filter out irrelevant individuals when preparing skeletal data, prioritizing individuals who are more likely to play a significant role in group activities and enhancing temporal consistency of the obtained skeletal data. The research paper proposes a novel skeleton-based graph attention network, GAR, for recognizing group activities in sports, leveraging panoramic graphs. It presents experiments on two datasets, volleyball and NBA. For the volleyball dataset, the authors report multi-class classification accuracy, MCA, for group activities and mean classification accuracy, IMCA, for individual actions. They utilize YOLOV 8 for pose estimation and object detection, fine-tuning the model on a custom dataset for detecting basketballs and nets on the NBA dataset. The training and testing batch size is set to 16, with a warm-up strategy for the first 5 epochs. The learning rate decays according to a cosine scheduler after the 5th epoch. The authors compare their method with state-of-the-art approaches on both datasets, showcasing improved results in group activity recognition and individual action recognition. The proposed MP-GCN method achieves state-of-the-art performance on the NBA dataset, outperforming video-based methods with significantly fewer parameters and lower computational costs. In the weekly supervised setting, the method still achieves satisfying results, demonstrating its compatibility with both high-quality and noisy keypoints data. An ablation study on graph structure is conducted, where different graph settings are experimented on the volleyball dataset. The results show that the proposed panoramic graph structure, which includes both intra- and interperson connections, achieves a significant improvement of about 1.5% in MCA with tolerable increases in parameters and flops. The effect of the number of graphs, M, is also investigated, and the results demonstrate that M equals 12 obtains the highest accuracy, which is consistent with the typical composition of a basketball game. Additionally, the effect of object information is examined, and the results show that incorporating object keypoints into the graph structure leads to significantly higher accuracy, and that placing object keypoints separately from the multi-person skeletons results in lower accuracy. The panoramic graph structure is shown to be effective in capturing the relationships between people and objects in the scene. The results demonstrate the effectiveness and generalizability of the proposed panoramic graph, which can be applied to various graph-based human action recognition tasks. The proposed pipeline for skeleton-based group activity recognition addresses limitations in traditional human skeleton representations by incorporating human and object keypoints into a multi-person object skeleton graph using a panoramic graph convolutional network. This novel approach involves human and object keypoints estimation, tracking-based pose reassignment, and collective activity recognition. Experimental results demonstrate state-of-the-art performance on 3 datasets: volleyball, NBA, and kinetics. The TSNE visualization of the graph structures shows a clear separation of classes, indicating the effectiveness of the proposed method. The comparison with other skeleton-based methods on the Kinetics 400 dataset highlights the value of object information, suggesting potential for further improvement. Although the performance falls short of SOTA video-based methods, this gap presents opportunities for future research focusing on enhancing multi-person and object representations in uncontrolled environments. A comprehensive review of existing literature on skeleton-based group activity recognition via panoramic graph is presented, covering a wide range of topics including robust associations, multi-pedestrian tracking, sum-product networks for activity recognition, and cost-sensitive top-down, bottom-up inference for multi-scale activity recognition. The references provided include works on convolutional relational machine for group activity recognition, social scene understanding, and end-to-end multi-person action localization. The authors also cite papers on real-time multi-person 2D pose estimation, channel-wise topology refinement, graph convolution for skeleton-based action recognition, and a unified framework for multi-target tracking and collective activity recognition. The review highlights the significance of hierarchical relational networks for group activity recognition and retrieval, as well as hierarchical deep temporal models for group activity recognition. Overall, the authors provide a thorough examination of the existing literature on skeleton-based GAR via panoramic graph, covering a broad range of topics and approaches in the field. This paper provides an extensive review of various techniques and models used in group activity recognition, focusing on the role of skeleton-based graph attention networks. The authors highlight the importance of understanding human interactions and group activities, which is crucial for applications such as surveillance, healthcare, and social media analysis. They discuss the challenges associated with group activity recognition, including the complexity of human interactions, variations in group size, and the need for robustness against occlusions and pose ambiguities. A comprehensive overview of existing approaches is presented, covering both traditional computer vision methods and deep learning techniques. This includes the use of spatial-temporal graphs, graph convolutional networks, and transformers for modeling human interactions and recognizing group activities. The paper also reviews several datasets commonly used for evaluating group activity recognition models, such as the NTU RGB plus D120 dataset and the Microsoft COCO dataset. The supplementary material provides additional details on the keypoint acquisition process, including pose estimation and tracking, for the Volleyball weekly supervised and NBA datasets. It utilizes the pre-trained Yueran 8X pose model to estimate human skeletons, following the official implementation of Yueran 8X. The visualization of the skeletal data used in the experiments is presented in Figure 1. The distribution of the number of individuals extracted in each frame from the Volleyball and NBA datasets is illustrated in Figures 2a and 2b, revealing that the number of individuals frequently exceeds 20 in many frames. This underscores the necessity of adopting a reassignment strategy to accurately track important individuals across frames. For the NBA dataset, the keypoints of basketball and basketballnet are extracted using the YOLOV8X model, fine-tuned for 50 epochs on a custom dataset. A comparison of the flops for RGB backbones used by prior works and YOLOV8X is provided in Table 1. The results indicate that YOLOV8X is more efficient than backbones such as VGG16 and VGG19. This is particularly relevant for the task of skeleton-based action recognition, which only uses an off-the-shelf pose estimation model. The research paper discusses the development of a skeleton-based GAR system using a panoramic graph, focusing on the distribution of individuals in frames from Volleyball and NBA datasets. It introduces a reassignment strategy for tracking issues, enhancing the accuracy by approximately 1.3% compared to selecting by maximum confidence. The system's performance is evaluated using various input features, including joint coordinates, bone vectors, joint motion features, and bone motion features. The results indicate a marked improvement in performance when combining the reassignment strategy with a tracking algorithm. The study contributes to the field of skeleton-based human action recognition, emphasizing the importance of efficient tracking for accurate action recognition. Additionally, the paper presents a novel approach to skeleton-based action recognition using a panoramic graph, introducing a multi-person graph structure that leverages both joint and bone features, along with motion features between consecutive frames. This structure is fed into 4 separate input branches, achieving higher accuracy than other keypoint-based methods. The paper presents a novel approach to group activity recognition by leveraging a panoramic graph structure to model complex interactions between individuals in a group. This method is applied to both fully supervised and weakly supervised datasets, with the latter lacking ground truth detection boxes. In the fully supervised setting, the proposed method achieves the highest performance on both datasets, outperforming baseline models and demonstrating the effectiveness of the panoramic graph structure in capturing group activity. However, when applied to weakly supervised datasets, the overall accuracy decreases due to missed detection and inaccurate tracking of key actors. The authors also present additional qualitative results, including an exploration of various interbody graph topologies and their impact on recognition capabilities. They experiment with several connection strategies, such as fully connected, linear, and pairwise connections, finding that the pairwise connection strategy achieves higher accuracy and brings a more stable training process. Furthermore, the authors provide ablation studies on network modules, illustrating the significant contributions of each component to the model's recognition capabilities. Additionally, the authors explore the effectiveness of various network modules and interbody links in a skeleton-based graph attention network for action recognition. They find that the combination of input branch, joint momentum, and body momentum, J plus B plus JM plus BM, yields the highest mean class accuracy, MCA, on the Volleyball and NBA datasets. The pairwise interbody link approach is found to achieve the highest MCA, surpassing other link methods, including fully connected and linear links. The authors also examine the effect of input dimensionality on MCA, demonstrating that incorporating visibility information into the input data improves MCA by over 1% for both 2-dimensional and 3-dimensional input data on the NBA dataset.